IB physics, and I'm pretty sure it also does in AP physics. It's a law that says electromagnetic wave coming through an unpolarized electromagnetic wave coming through non-M. So today we're going to be talking about the Malus law, and it's a law that says whenever you have a polarizer and an unpolarized light going through it, you're going to get a half intensity coming out of it. And this appears both in IB and AP physics. And if you are a curious student, you may be wondering why this is the case all the time. Why is it exactly a half of what it was before it went through the polarizer? So I'm going to be deriving this law using integration techniques, which is going to be pretty fun because it's a combination of the two most important STEM subjects, maths and physics. So let's get into it. So you have a polarizer, like that. And let's set the polarizing angle like this. It doesn't really matter, it doesn't affect the value when the light goes through it, how much like it reduces. And you're gonna have unpolarized light going through it. And it's gonna be in all these different directions. And we know that, let me draw another one to see more clearly. If you take one of the rays like that, the polarizer is only going to let through the vertical component of this magnitude, and that is going to depend on this angle here. Let's call it theta, and let's call this magnitude x, and then by the Pythagorean law, this length, which is the magnitude of the ray that comes out of it, will be x times cosine theta. And we know that this is just the amplitude of the rays, and we also know that the intensity is the square of those amplitudes. So after if you only take this particular ray, it's going to come out to be the square of the amplitude we just gained. But the thing is, we have infinitely many rays like this in all different directions, and so it's pretty fair to assume that these rays are kind of spread out among all different angles by the same density, like I draw at first, like this. So this is why we need integration to rigorously prove the Malus law. So if you look at this angle, and if you consider when the angle is between 0 and pi over 2, the reason why we set it at pi over 2 is that we don't want this cosine theta to be negative. Then the integration would be more complicated. And it's okay to do this because what happens on the upper half, it's the same thing that happens on the lower half. So if the Malus law applies for the rays that's between these angles, then it's fair to say it's the same for all 4 different directions. And so this integration, this symbol means the sum of intensity